Okay. So the paper presented is named Walle. It is a large-scale production system for the device cloud collaborative machine learning, and it is proposed by the Alibaba Group and has been used in the application, for example, the Taobao or the Xianyu. And the first part is the background and the motivation. The paper proposed that the existing mainstream cloud-based machine learning framework need the users to upload their raw user data to the cloud, and then the cloud can do the computation or do the training, and then return the calculation results back to the server. And then in that case, the mobile devices function only as the user's interface. And here is three key problems. The first one is the high latency. For example, in the live streaming scenario, the users want the low latency feedback from the server. But if they need to transfer their video data to the server, the latency may be high. And the next part is the high cost and the heavy load. For the users, if they don't have a Wi-Fi, they will use a lot of data usage to upload their raw data to the server. And for the server, they need to store all of the users' data, and it will cause the high cost. And the last problem is the high privacy risk. It means the raw data of the user data contains a lot of private information, and upload these sensitive data to the server is not safe.
Can you give me give us a more solid example about the example in the left side figure? So actually, what kind of user data we are trying to upload into the cloud, and what kind of results will be returned? From the figure, it's like some gestures, right? But why the results are like some clothes? I don't know. Do you have an example?
For example, the authors used in the experiment, they said if we, for example, in the live streaming, we want to recognize the highlight in the live streaming video, for example, the items or the face of the users. And if we use the cloud-based framework, we need to upload all of the videos to the server, and then the server can do the face recognition and then return the recognition results back to the user. But here we want to do the recognition in the mobile devices of the users, so to save the communication cost and also to reduce the latency.
Okay, I see. Thank you.
And so to overcome the three bottlenecks, we need to generate a new device cloud collaborative machine learning framework. And here, because the users is close to the users' mobile devices is close to their user data, so we want to take advantage of these mobile devices to do the calculation. And the existing works was on the algorithm layer. But how to build such a system in the system layer is still an open problem. And this paper proposed to generate a large-scale collaborative machine learning in the layer of the system. The next part is the overall goal and the architecture of the Walle. The overall goal of the Walle is to support the general device cloud collaboration and to generate an end-to-end framework. Because this framework is focused on the industry, so there are hundreds of CV, NLP, or recommendation tasks in a large-scale production, and different users, of course, has different mobile devices. So there are heterogeneous hardware and the software for these mobile devices, and also different company can have different kind of cloud servers with different operating systems. So the framework will face three kind of challenges. The first one is the execution challenge. First challenge is the long iteration cycle. It means in existing machine learning framework, the machine learning tasks is released to the users with the application update, but most applications are updated weekly or monthly. So, but the machine learning tasks require frequent experiments. So this is the first problem. The second one is, just as I said before, the heterogeneous backends include the server and also the mobile devices. And the third challenge is the diverse machine learning tasks. For example, the model structures can be diverse, including the CNN, RNG, or something other. And also the mobile devices used by the users have limited device resource. And here is an example for the mobile Taobao. The maximum RAM is only 200 megabytes, but so the package size cannot be exceed 300 megabytes. So here is the first execution challenges. And the second kind of challenge is the input preparation challenges. In the realistic scenarios, the user behavior data can be typical, so it cannot be pre-proposed by the standard libraries, and also different machine learning tasks need have diverse trigger conditions. So how to efficiently manage these multiple trigger conditions is a problem. And the third kind of challenges is the deployment challenges. First, the machine learning task need to deployment to massive devices with massive tasks. And also different device has the availability of different devices is different. For example, some mobile devices have unstable wireless connections, and here are only one application can run on the foreground. And the last one is the potential task failure. If the machine learning task failure, the whole application will be impacted. So here is to solve in the deployment of the system. So focus on three kind of challenges. The system is divided into three parts. The first part is the compute container. It focused on the execution challenges. And the second one is the data pipeline. It focuses on the input preparation challenges. And based on the compute container and the data pipeline module, there are deployment platform. It focuses on the deployment challenges. So here is the first part, the compute container. Here is the four challenges I mentioned before: the update challenge, the heterogeneous challenge, and also the resource limitation and diverse machine learning tasks. Based focus on these four challenges, the authors propose a kind of new deep learning framework named MNN, and it is open source and contains a new designed tensor compute engine. The designed tensor compute engine include geometric computing design algorithm and also a semi-auto search algorithm. The geometric computing algorithm is to reduce the workload of the mobile devices, and the semi-auto search algorithm is to use to find the optimization backends to execute the machine learning tasks. And based on the designed tensor compute engine, the authors propose some libraries, and also each machine learning task will need to be executed in virtual machine. So the authors designed a Python thread level virtual machine, and based on the virtual machine, there are some standard API. So here is the first part, the compute engine.
Honglu, can you go back to the previous page? So from this architecture, it's like the input will be the machine learning task scripts, right?
Yes.
Because this architecture designed to address the problem, say, because the mobile app is not like updated every day, right? But the machine learning workflow, people may want to update the machine learning task, update the training, model or other settings. So it's like if we wanted to push new machine learning tasks to the user mobile phone, we don't need to update the mobile app. Instead, we just push the machine learning task script to the user mobile app, right?
Yeah.
Because the user mobile app is like is built with the MNN framework, like all the APIs, like thread level virtual machine. So the MNN framework can take the machine learning task script as the input and do the training or inference, right?
Yeah.
Okay. But why we need to have the Python thread level virtual machine?
The Python thread level virtual machine focus on the concurrent task execution.
Is it because I remember you mentioned the one challenge is the mobile app is running in single process.
Yeah.
And if the process failed, the app will crash. So is that why we need to have the Python thread level virtual machine to, avoid crashing the whole mobile app?
And besides, because only in the applications, there is the GIL, so only one thread can be executed in one process at the same time. So the authors proposed a new Python thread level virtual machine to make sure that there can be multiple machine learning tasks executed in the one application at the same time.
Okay.
And here is the first part, the computer engine. It concludes two parts. You can see the geometric computing and also the semi-auto search algorithm. And this one is the geometric computing, is to solve the manual operator optimization problem. And the second figure is the is the semi-auto search algorithm to solve the graph level runtime optimization problem. Here is the geometric computing. The key idea of this computing is to replace the transform operators and the composite operators with the atomic operators. The atomic operators mean the simple calculation, for example, the plus or multiply, and the transform operator can execute for example, the reshape operation, the slice operation, and the composite operator can do it can be decomposed into the atomic operator and the transform operator, and then it can finish the work of pulling normalization or the 3D convolution. And you can see if we have the NBA means the number of the backends here is the 16. And the NAOP means number of the atomic operator. The TOP is the transform operator. COP is the composite operator. And the FOP is the control flow operators. So here, if we use all of the 4 operators, the complexity of the 16 hardware backends is the 1954. It means in each backend, it will do some atomic operation, some transform operation, and also some composite operation. But here, if we can replace the transform operation with one atomic roster operation, it's kind of new design atomic operation. So we can reduce the computation complexity from 1954 to 1055. Because for each backends, they only need to do the atomic operation, and here is the server can still do the transform operation or the composite operation, and also the control flow operation. So the workload of the mobile devices can be reducing by 46%. So the key problem is how to design the atomic register operator. So here is the basic functionality of the transform operator. It is to move an element from a memory address to another memory address. If we see it from the view of the geometry, is to transform the coordinate of the element of the element to another coordinate. So since the transform operator has this basic functionality, we can use the simple atomic operator to calculate the movement of the memory address. And here is an example. If we use the slicing operation as an example, A is a 2 times 4 matrix, and the second row is need to be sliced as B, and B is a 1 times 4 matrix. So for an element in the matrix Bij, its relative memory identifier is I times 4 plus j. And because of the definition of the slicing operation, the Bij equals to the AI plus 1j, because A is a 2 times 4 matrix. And so the coordinate of the element AI plus 1j in A is the I plus 1j, and the relative memory identifier is the I plus 1 times 4 plus j. So here we can use the use the list operation to realize the functionality of the slicing by iterating the coordinate ij, and move each I plus 1j to the bij. So if we can optimize if we can replace the transform operators and also the coordinate operator with the atomic register operator, we can reduce the workload. And also based on the atomic operator, we can also do some other optimization. First, in the algorithm level, the authors choose some more efficient algorithms, including the Vinograd and the Streisand algorithm. These two algorithms are used to are two efficient algorithms in the matrix multiplication. And also there are some other level optimization, for example, the ISA level, the memory level, and also the assembly-based optimization. So since we can reduce the workload in each mobile devices, we can move to the next problem. The next problem is that the heterogeneity of the backends. Here we can see the machine learning task to be a series of operators, and there are some available backends, and each backend may have different hardwares and also different softwares. So how to quickly find the mini-cost backend is a second problem. Here is the formulation. First, the series of n operators is the OP1 to OPn. And the cost of the backend BA can be seen as the CBA. It is all of the it is the cost of each operator in the n operators on the backend BA. So the goal of the semi-auto search is to find the backend with the minimum cost. It means how to find the optimized backend BA to has the meanest CBA. And here, because we can compute the cost of each operator on the backend BA. Here the ARGS is all of the feasible implementation algorithm with the optimal parameters, and the QARG is the calculations in the algorithm ARG, and the PBA means the performance of the backend BA. And the PBA means the calculation number per second can be executed in the backend BA. And the SARG BA means if we execute the algorithm on a GPU backend, we need to transfer the data from the memory to the GPU memory. So as evaluates the transmission time. So here is the problem to compute the COPI BA. And here we can change it into an optimization problem. So the objective is to minimize the computation of the memory cost. And here we have some constraints, include the packing size in the SIMD, the tail size in the matrix multiplication and the block unit and in the algorithm, and also the reduction of the elementary calculations using the Streisand algorithm. So here we can formulate the formulate the search problem into a optimization problem, and it can be solved in reasonable time. So here is the second part of the tensor computer engine. Any problems here? Okay, so based on the proposed computer engine, then the authors design some libraries. For example, the scientific computing and the image processing library. The scientific computing includes the function like array creation and the binary operations, and the image processing includes some operation include the image filtering and so on. And also the MNN also provides the model inference or the model training libraries. So after we design the computing engine, if the application on different mobile device want to do the machine learning tasks, it need to execute the task in a Python virtual machine. So here the authors choose the widely used Python compiler and the interpreter called the CPython. But there are still some problems for the CPython. The first one is the size of the package is very large. And the second problem is that the CPython does not support the multi-threading to improve the efficiency because of the GIL. The GIL allows only one thread to be processed at the same time within a process. And as I said before, each application is one process. So there are only one thread can be processed at one application at the same time. So focus on the first problem. The authors choose to tailoring some functionality for the CPython. Because the compile operation can be executed in the server, so the server can do the compile and then send the bytecode to the CPython interpreter in the mobile devices. So the authors can tailor all of the compiler functions here. And another is for the library and the module tailoring. The authors keep only 36 necessary libraries and 32 necessary modules. Then they can reduce the size of the CPython packet from more than 10 megabytes to 1.3 megabytes. And for the task level multi-threading, because of the GIL, only the applications cannot do the multi-threading training. So here the authors abandoned the GIL, and here you can see in this figure, here is the refined framework here. And you can see at the same time there are 3 interpreters, and each one has a thread to do the machine learning task. But if we want to execute multi-threads in the process, we need to solve two problems. The first one is the virtual machine isolation. The second one is the data isolation. For the virtual machine isolation, the authors modified the creation of the VM instance. Specifically, they modified the initialization of the C Python. And for each thread, they can create and initialize a PyInterpreter state instance. And this can be seen as a Python virtual machine. And to solve the data isolation, they adopt the thread-specific data technique for the data isolation to make sure that the data from the one thread can only be accessed by itself, cannot be accessed by the other thread. So here is the first design part to solve the execution challenges. Now is the second design part, is the data pipeline. Here you can see from the figure that in the mainstream data pipeline, the authors need to upload the basic events to the cloud. But here, if we want to deal with these events, we only want the server to transfer some task triggers to the devices. So the key design goal is to support the stateful computation over the unbounded data stream on only one single device. And to support the design, there are a few proposed design. First one is the event sequence creation. So there, in the device side, there are 5 major kinds of basic events. For example, the page enter, page scroll, and the click and the page exist. And each kind of the event is recorded with the event ID, a page ID, and the timestamp and the event contents. So it can be changed into a time level event sequence. And also the page level event sequence is created by aggregating the events between the enter and the exist events of the same pages. Here is the event sequence creation. And the next one is the trigger management. Because there are a lot of machine learning tasks, and the different tasks can have different kind of triggers. So if we want to use a list to storage the triggers, it will high time cost. So the authors here use the try to for efficient trigger management. And for the task execution, besides the standard data processing and the model execution APIs, the data pipeline also provides provides 4 more functions to deal with the events. It is the key by time window, filter, and the map. And for the collective storage, because each tasks, the output of each stream processing task is very small, and it is saved as a table using the SQL. If the device finish one task, it transfer the task to the server, it will be a kind of communication resource waste. So here the authors use a collective data storage API to reduce the number of write. It means when we collect a number of auto features, we can send it back to the server together. And the next part is the deployment platform. The deployment platform is to solve the deployment challenges, including the frequent experiment of the machine learning tasks, and also the massive task deployment requirements, and also the device availability, and also the potential task failure. Here, first, here is the workflow of the deployment platform of the system. And first, for the task management, the authors use Git to management the different tasks and also do the version control of the certain task. So the entire task management can be regarded as a Git group, and each business scenario corresponding to a Git repo. And each task can be seen as a branch, and each version of task can be corresponds to a type. And besides the tasks, the fields are also divided into two categories. The first one is the shared fields. The shared fields can be accessed by, for example, all of the users with the same version of the application. And another one is the exclusive fields. It can only be accessed by specific users. And for the task deployment, the Walle provides two kinds of policy. The first one is the uniform policy. For example, it can release the machine learning tasks by the application version. And the customized policy can support to release machine learning tasks to the users with some specific software or the hardware. And for the task release, the authors use a push then pull method. It means first the server will push the tasks to the server, and after the server finishes the task, it can add the local task profile into the HTTP header and add the cloud to compare it with the latest task profile. And besides, if a new task needs to be released and takes the uniform deployment policy, so the cloud can respond with the CDN address of the shared task fields. So here is the last design of the system to solve the challenges. And the next part is the evaluation results. The first is the performance of the Walle in e-commerce scenarios. Here, the machine learning task is the highlight recognition. The highlight recognition means in the live streaming, for example, the recognition can be the items in the hand of the woman, all the face recognition. If we use a cloud-based design here, we need to transfer all of the live streaming videos to the server, and then the server can do the highlight recognition and then send the results back to the mobile devices. So because of the communication cost, the cloud-based design can only cover parts of the streamers and also can analyze part of the video frames. But if we use the mobile devices of the streamers to finish the highlight recognition here, we can reduce the cloud side load and also cover more streamers. And the daily recognized highlights per unit of the cloud cost can be improved. And you can see the results here. For kind of detection or recognition, the latency per highlight recognition is less than the 150 milliseconds. And for some highlights which cannot be recognized by the mobile devices of the streamer, the mobile devices can also send it to the server to finish the recognition. And the next page is the production use of the Walle system. It has been used by the Alibaba since 2017 and has been run for more than 1,500 days. The second figure is the covered devices to the elapsed times, and you can see before the 7 minute. You can see before the 7 minutes. Before the 7th minute, the system needs some time to allocate the Walle system to all of the users. But after the 7th minute, they can normally covering the devices can be normally covered in the with the time. And the next part is the macro benchmark testing results. Here, the authors compared the MNN with the TensorFlow Lite and the PyTorch Mobile on different backends. Here include the ARM and the OpenCL Metal and the CUDA. And you can see the inference time of the MNN is less than the TensorFlow Lite and also the PyTorch Mobile. And the next experiment is the performance of the Python thread level VM. Because CPython has a GIL, so the performance of the Python thread level virtual machine is better than the CPython. You can see if the latency is less than the 100 milliseconds, it is the lightweight task. The performance can be improved 52.11%. And for the middleweight, the performance can be improved 144. And for the heavyweight tasks, the performance can be improved by 25%. And the next figure shows the real-time turnover of with the varying size of data upload. The real-time turnover is in the end of the data pipeline, and it will transfer the features to the server. And you can see when the upload is less than the 3 kilobytes, the delay can be less than the 250 milliseconds. And even if the size of the uploads is equal to 30 kilobytes, the delay can also be less than the 450 milliseconds. And so the Walle system can realize the low latency aim. So here is the last page of the presentation.
Okay, thank you, Honglu. Anyone has a question?